Okay, today we are going to be talking about section 3.1, extrema on an interval. This is part one of this topic. First of all, an extrema is just a way of referring to maximums or minimums with one word. So when I say extrema, I'm talking about either a max or a min. Could also be multiple. We will get to some different forms. Today we're focusing on what are called global or absolute. I use those terms interchangeably. In the next video, we'll talk about what are either called relative or local, but today we're focusing on the global or absolute. So basically, I think for the most part, we understand conceptually what these things mean or intuitively. So absolute minimum would be the least point or value out of all the points that we're considering. If we're looking at notation, what we're saying is the output f of c is less than or equal to all of the other values. On a domain, if we're talking about a whole function, and I'll talk more about that, or a specific interval. The specific interval will be kind of our focus for today, which I'll talk about in a little bit. Absolute maximum, which once again intuitively is greater than all the points, means f of c is greater than or equal to all the values f of x for all x in a domain or specific interval. Now, when we talk about a particular domain, not all functions have a global or absolute max or min. Some have one and not the other, or none at all. So for instance, if I gave you a function like y equals x to the third, right, that looks like this. If we look at the whole domain here, that has neither a max nor a min. Or if we look at something like y equals x squared, okay, that has an absolute min, but not an absolute max. By the way, when we talk about absolute maximums and minimums, we're actually talking about the output. So we would say the absolute min of this function on its domain would be 0. Okay, so it occurs at 0, but I'm talking about the output, which is 0. So if you're ever asked what's the absolute maximum or minimum function, you actually give the output, not the input. If I ask where it occurs, it would be the input. Okay, just some things we're going to get used to as we see these examples. And then we do have some functions that have both, right? So let's think of one that has both. Let's think of our semicircle y equals the square root of 1 minus x squared. So this has an absolute max of 1. It occurs after 0, so our absolute max would be f of 0, which is equal to 1. Our absolute min is 0. It just happens to occur at two different places. So it occurs at -1. It also occurs at 1. But the maximum or the minimum value, absolute minimum value, is the output, which is a 0. Okay. Okay. So that's if we're talking about the domain. So sometimes functions have both an absolute max and an absolute min. Sometimes they have one or the other. Sometimes they have neither. Okay. Next, we're going to be talking about on specific intervals. Okay. So now we're going to talk about the extreme value theorem. Well, sometimes I'll refer to this as the EVT. So in this particular case, if f is continuous on a closed interval a to b, and we'll talk more about some examples of this, then f is guaranteed to have both an absolute max and an absolute min. So let's start with a function that doesn't have either. So let's just take a basic cubic functions. Looks like this. This has neither an absolute max nor an absolute min. If you're thinking that's a max and that's a min, that is true. But that's what we call a relative or a local, and that is not our discussion for today. We're talking about a point that's greater than all the points, which would be an absolute max, or a point that's lesser than all the points, which would be an absolute min. Now, if I take this, now that's the whole domain, but if I take this and now I bound it, let's say on an interval here, okay, so let's say I give you something that looks like this, okay, so I give you, let's draw that again. Let's say this is A and this is B. Now, as long as that's continuous, it's guaranteed to have both an absolute max or an absolute min. So in this case, we have the absolute max here. So let's say this is occurring at, call it C. Let's give it a point here. So we would say that f of c is the absolute max, okay? And in this case, f of b are what we would call the absolute minimum, okay? So just so we're clear, we are either going to have, and these are what are called critical points. On the interior we have these critical points, and I'll talk about that here in a moment, or the endpoints. Those are our potential. So as soon as we put our function on that closed interval, we're guaranteed to have an absolute max, we're guaranteed to have an absolute min, and those things would occur either at the endpoints, would be potential, or these critical points, which I'll define here in a moment, okay? Now, if you're thinking, what if a function is a horizontal function? Sometimes people, so let's say I just had a horizontal function. Let's say this is at 2, and let's say I'm looking from 1 to, let's say, 4. So we're looking at the horizontal function, f is equal to, or constant function. That, someone might think that doesn't have a max nor a min. If you look at the definition in your notes, remember I said that we would say this is f of x, or f of c is a max if it's greater than all of the values f of x on a particular interval, in this case 1 to 4, that would be a max. Well, the key here is a greater than or equal to. So actually our absolute max is equal to our absolute min. They're both the same, and that is 2. So both the absolute max and min are 2 because it's greater than or equal to or less than or equal all the points. It just happens to occur on the entire interval, okay? So once again, it's important that we think about the absolute max or min. It's like if I had a classroom filled with students who were all 16 and there's nobody who's younger than that and there's nobody who's older than that, then the maximum age of that class would be 16 and the absolute min of that class would also be 16, okay? Also, another thing that we sometimes get confused is, let's say I have like a sine-like function, and whether I'm looking at an interval or I'm looking, for the whole domain, right? We get something that look like this. In the case of sine and cosine, for instance, it has one max. That maximum value would be 1, right? The absolute maximum value would be 1. The absolute minimum value would be -1. In both cases, if we're talking about the domain, it just occurs an infinite number of times. So a max or min can occur multiple times, but there can only actually be one absolute max and one absolute min. Okay, so let's talk about critical points and how we're actually going to find these things in a algebraic example. Okay, critical points. Critical points are when a function is continuous at that particular point. That's definitely important. If f prime of c is equals 0, so horizontal, and this is something that we've been talking about since way back in September, or f prime of c doesn't exist, and if you think about like an absolute graph, that kind of tells you what we're talking about there, then f has a critical point at x equals c. Now, critical points aren't guaranteed to be maxes or mins, they're just potential. Same is true for endpoints if I'm looking at an interval, which is really going to be our focus here. So when we talk about when we're looking for absolute max or mins, we want to consider all endpoints and we want to consider any critical points. So once again, just so we're clear what a critical point is, so if I look at a function like this, right, so we would have the absolute min here, we'd have the absolute max here, and the absolute max, we have a critical point where f prime of c is equal to 0. So we'd have our absolute max, but it doesn't guarantee. So for instance, if I had something like, this, right, I have my absolute min is at that endpoint, the absolute max is that endpoint. I had potential, because there's critical points both here and here, but in those cases they weren't absolute maxes or mins. Now the same is true, we have to consider for something like y equals the absolute value of x. Okay, so y equals the absolute value of x looks like this, and we obviously have a minimum there, and that's when f prime of 0 does not exist. So those are also critical points, as long as it's continuous, right? Because if it's not continuous, the derivative still won't exist, but that won't be a critical point. All right, so let's look at examples and see how we're going to find these things. Okay, so what we're going to do is actually finding these things. So find all critical points, then determine the absolute extrema on the interval. So remember, as long as the function is continuous, which it says, by the way, polynomials are always continuous, we know that we are both going to have an absolute max and an absolute min on any closed interval. So we're guaranteed this is going to be in existence. And once again, where we look is the endpoint. So I already know I'm going to consider f of -1, I'm going to consider f of 3, but then I also have to find the potential on the interior, which are those critical points. So in order to find the critical points, we're going to go ahead and take the derivative of this. And I get one critical point. Now, if it was outside the exterior here, it is a critical point, but it wouldn't be for this particular example because we're only looking on this interval. So this is a critical point because the derivative is equal 0. It does not mean that it's an absolute max or min, or even a relative. It just means that there's potential for that. Okay, now what I'm going to do is actually going to compare these outputs. Since I know an absolute max occurs and I know an absolute minimum occurs because it's continuous on a closed interval, I know that the absolute max will be at one of these 3 points and the absolute minimum will be at one of those 3 points. So what I'm going to do is take these candidates, if you will, and I'm going to plug these all into F. And you know, this is something I have to do without a calculator, so I don't need the graph. I just know that these are the possibilities. So if I take -1 and plug this in, I get 1 plus 4 plus 5. Maybe I have to check my arithmetic. So that's equal to 10. 2, that goes in, that's 4 minus 8 plus 5. So that's -4 plus 5. That's equal to 1. Okay. 3 goes in, that is 9 minus 12 plus 5, so that's -3, that is 2, okay? And now we have everything we need. We know this is the absolute max, we know this is the absolute min. So absolute max is f of -1, which is equal to 10. Once again, we would say it occurs at -1 if that's the question, but the actual absolute max is the output, which is 10. The absolute min occurs at 3, and f of 3 is equal to, no, wrong one, okay? At least I caught it this time. Okay, so the absolute min occurs at 2, f of 2 is equal to 1, and that is my absolute minimum, okay? We're gonna do one more example, and that will be it for this video. Okay, example 2, this is our function here. This one's gonna give us a critical point because the derivative doesn't exist. This thing is always continuous. I know that might not be obvious to you, but keep in mind, we're squaring this thing and taking the cube root. If this was a square root, if we had this flipped, then we would have a domain issue and it wouldn't necessarily be continuous. But this thing is continuous for all reals, so it's definitely continuous on that domain. Okay. So once again, we're looking for all the candidates. So we already know that -1 and 3 are candidates, but then I also have to find critical points. So I'm going to take the derivative of this, which is 2 minus 2/3 comes down, that leaves us with 2, and then x to the -1/3. Now, as soon as I see this x to the -1/3, you know, when we've been turning out derivatives, we leave things like this, but to really see what's happening here, we do want to rewrite this thing. So realize what we're talking about here, f prime of x is equal to 2 minus 2 over the cube root of x. And what I realize is, this thing does not exist at x equals 0. So before I do any algebra at all, I know this thing doesn't exist. It does exist in the original. It is continuous at x equals 0. You can take 0 to the 2/3 power, you get 0. But here we have 0 in the denominator. So we have a critical point. We're actually going to have 2 here. One is going to be at x equals 0, and we would state because f prime does not exist, okay? Now our second critical point comes from because the derivative is 0. Now I do have to solve it. The easiest way to solve something like this is get the fraction on the other side. So we get 2 is equal to 2 over the cube root of x. We can multiply both sides by the cube root of x, divide by 2. So what I end up getting is the cube root of x is equal to 1. And what that means is x equals 1. -1 doesn't work because -1 would be -1. Keep in mind, cube roots retain negatives. So these are our two critical points. So this one we get for when f prime is equal to 0. Okay, so we actually have 4 candidates in this case. So x, f of x, okay, and we have -1, 0, 1, and 3. And by the way, if we get critical points, once again, I think I mentioned this last time, but just to reiterate, that are outside this interval, we wouldn't be considering them for this example. Now, for all of these, we're going to plug these back in the original. Don't be thrown off by the x to the 2/3. Keep in mind, x to the 2/3 means I'm going to square it and then take the cube root. Or if it's a large number, I'd want to take the cube root first. This isn't going to be a big deal here. So take -1 and plug it into this. I'm going to get -2, okay, minus, and then if I plug -1 into this, -1 squared will be 1, right, +1 and 3, so that -1 becomes 1, so this will be -2. Oh wait, I'm sorry, the derivative here. So let me start over. No, I got that right. So -2 goes in, that gives me -2, I apologize, -3, and then -1 to the 2/3 power, because of the squaring will be 1. So this gives me -5. Okay, now if I plug 0 in, well that's easy, that thing just zeroes out. 0 to, -0, so that is just 0. 1 goes in, 1 to the 2/3 power is just 1, so I'm getting 2 minus 3, that's equal to -1, okay? And then finally, if I plug 3 into this one I'm gonna have to think through a little bit. Unfortunately, without a calculator, we do have to think about what's happening here. So I get 3 goes in, that gives me 6, minus 3, and then 3 to the 2/3 power. So let's square that, so that's the cube root of 9. Now, what we have to do is, we don't have to know exactly what this value is, we just have to be able to consider what it is. So if you think about this, if this is the square root of 9, this would be 6 minus 9, that would be like -3. But instead it's the cube root of 9, so that is going to be basically between 2 and 3 here. So it is actually, so it's definitely going to be negative, right? But, so it's not going to be the absolute max, because 0 is the absolute max here. But it's not going to be as low as -5, okay? So what that means is it's neither going to be the max nor a min. So that's really all I have to think through. A little bit tough without a calculator, but we do have to have some number sense when it comes to these things. Okay. So the absolute max, once again, it's the output. So the absolute max is 0. It does occur at x equals 0. So that's our absolute max. The absolute min is -5. It occurs at x equals -1. Hopefully that's still in range. Okay, so absolute max is 0, absolute min is -5. Okay, so that's the first part of 3.1. We'll be doing another video where we're getting into the whole idea of the relative or local max and mins later.